Okay, so in this video, I'm going to talk to you about double replacement reactions and talk to you about how to predict the products for double replacement reactions. Okay, remember that a double replacement reaction is going to occur between two ionic compounds and they're going to basically switch partners. Okay, the reactants have to be two ionic compounds. That's very important. And double replacement reactions usually will occur in an aqueous solution, meaning both of the ionic compounds we start with will usually be aqueous. So, how does this work? Basically, you can view it two ways. The positive ions changing places, or if you really want to, you could view it as the negative ions changing places. Remember, we called it our swinging, dancing, married couple. All right, so you have to check and make sure that once you've created your products that you have crisscrossed or swapped and dropped to make sure you have the correct formulas. Okay, so double replacement reactions have three driving forces, so they only occur if one of the three things occurs. Okay, so one, we form a solid, meaning one of them doesn't end up dissolving. So that solid would be called a precipitant. So we form a solid, or we form a gas that bubbles out, or we form a covalent compound, which is typically water. If one of these three things happens, the reaction happens. If none of these three things happen, the reaction does not occur. This is our general recipe. We do technically have two, but they both follow the same kind of format. So we have A and B meeting with C and D, and notice A is now with D and C is now with B. It's important that you keep the positives at the beginning, right? So A and C are both the cations, B and D are both the anions. So notice how A is now with D because A has to be a cation with a new anion, and C is now with B because C is a cation that has to be with another anion, which is B. Okay, acid-base neutralization is the same kind of concept. We're still switching in the same exact kind of pattern. So here's our first example. We have sodium hydroxide and iron 3 chloride. So we know that the sodium and the iron, which are both the metals, which are both the cations, are going to switch places. So we flip them around and then we check if they get to be crisscrossed, or we check our swapping and dropping. So we see our sodium was with hydroxide. So now our sodium is with the chlorine, which used to be with the iron. And we see the iron is now with the hydroxide that used to be with the sodium, and it's now with the iron. We swap and drop. Notice this 3 came from iron being +3. Remember, this 3 belonged to the iron being +3. And then sodium chloride +1, -1. That's how we end up with that formula. Okay, and so if you take a look at this, this is what happened. Just to kind of reiterate, this was +3, -1. That's how we end up with this formula. +1, -1. That's how we end up with that one. All right, at the end, you would balance this. So we'd put a 3 here so that we have 3 chlorines. Then we put a 3 here to have 3 sodiums and 3 hydroxides. That would balance it out. All right. Notice now we have to take a look at both of these products. We have to figure out if this reaction occurred or not. So none of these products are immediately a gas. Like it's not like carbon dioxide or carbon monoxide. And also neither one of them is water or covalent. Ionic, definitely metal, nonmetal. Ionic, definitely metal, nonmetal. So now we have to think about how do we know if this reaction occurs. This is a point where we take a look at our solubility rules on page 6 of our chemistry reference tables and determine if it's a solid. So looking at this, we have to figure out if either one of these are solids. So if you take a look at this, the solubility rules, the side on the left states that if it follows that rule, it will be soluble, and on the right, it will be insoluble. So there's a rule that states that group 1A salts are soluble. So therefore, we automatically know this guy is aqueous. It's soluble. It dissolves. All right. But the other rule on the insoluble side states that all hydroxides, so we have one of those, are except those that are group 1, strontium +2, barium +2, and ammonium +1 are insoluble. So iron is not any of those exceptions, so it follows this rule that states that all hydroxides are insoluble. If you're insoluble, you do not dissolve. Therefore, you are a solid. Therefore, it's a precipitant. Therefore, this reaction does occur. Remember, we just have to have one of these 3 things, right? One of these 3. Either it forms a solid, forms a gas, or forms a covalent compound. So in this case, it formed the solid, and we now know that because of the solubility rules off of page 6. Okay. So that tells us the double replacement reaction occurs. Double replacement reactions at their heart are not very difficult. It's a matter of just switching your partners. So what I tend to do is at the beginning, I tend to circle and square. So I circle my two cations and I square my two anions and I swap them so that I still have a circle square together and a circle square together. That might help you just to kind of walk through it. And then at the end, you swap and drop and consult your solubility rules. Okay, so this is how we predict products for a double replacement reaction. So now that you've watched this video, go ahead and take a look at your practice and go ahead and see if you can predict the products for a couple of double replacement reactions.